Hello, welcome back. So, we already covered the majority portion of integration, and so this video will be wrapping up integration and sort of covering up the bits and pieces that weren't covered in the previous videos. Right. So, starting off, let's say there's some graph y equals 4x squared, let's say. And by now you would already know how to get the area under the graph bounded by the x-axis, right? That would be just your normal integration, right? So let's say if you want to find the integral and for this region, you just integrate it from 0 to 1 and that would give you this area, right? So now let me change my question and ask you that okay, so when I plug in 1, y value is 4. Now let me ask you that instead of this area, now I want this area, right? So instead of wanting the area bounded by the x-axis, now I want the area bounded by the y-axis. Right, so the way you do this is that first you make x the subject, or you make x a function of y, right? So y equals 4x squared, and your goal is to get this, right? And you would realize that this is very similar to finding an inverse, and just instead you don't swap the x's and the y's. Right, so let's divide both sides by 4 and then let's take the root, and I will take the positive root because I am taking the portion that is to the right of the turning point, right? Remember this from quadratics or functions. So now I got my x as a function of y. Right now, why did I do this? So normally what we did previously was that we took some changes in x, dx, and the height at that point was y. And so we said that y multiplied by dx will give us the area of this rectangle, and summing up all the rectangles will give us this area. Right, so now what I have done is that now what I can do is that I take some change in y, so dy, and I multiply that by the x value at that point, and so I will get the area of this. Right, so x multiplied by dy, and then I sum up all of these, so integral from 0 to 4. Right, I am taking the y values instead of the x values because I am taking changes in y. Right, so also remembering that this, once I sum up all of these rectangles, the area that I get will get closer and closer to the actual area under the curve once I take smaller and smaller dy's. Right, so I can use this essentially because now I have x as a subject of y. Right, so integrating from 0 to 4, x is a function of y dy. Right, so 0 to 4 root y over 2 dy. Right, so taking the half over there, 0, 4 root y. Right, so now we differentiate, this should be y. So y half, you add 1 to the power 3 over 2, and then you divide by that power, so 2 over 3, y 3 over 2. Right, so y 3 over 2, 2 over 3 from 0 to 4. Right, so let's take the 2 over 3 out, so 1 over 3 y 3 over 2 0 to 4. This is 1 over 3 4 to the power 3 over 2 minus 0, which would be 1 over 3 multiplied by 8, which would be 8 over 3, and this is our answer. 8 over 3 is this yellow area. Right, so now we come to a part that's the only part that's new in AS math. So it wasn't in O level ad math, and now it is in A level math. Volumes of AS. I meant to write volumes of revolution. Right, so consider the following. Let's say, let's say Okay, now let's say there's this line y equals 2x, and of course this is the x-axis. And now what you do is you revolve this around the x-axis, right? So you're taking this and you're revolving it around the x-axis in the 3D plane. So once you revolve this, you will get something like this, right? And the question that we have to answer is that what is the volume of this shape once you rotate it 360 degrees around the x-axis, right? So this would be your this would be something that you can calculate by integration, but instead what we want is that once you revolve it 360 degrees around, you of course get a 3D shape, and the question is what is the volume of it, right? So of course, what I'm about to say would generalize to any curve, but just taking this, we know that if I take a thin section of this, let's say if I take this thin section, it will, if I take thinner and thinner sections, the section that I get will be similar and similar to. Okay, I took my time to draw it out. So once we take some sections of it, what we get is some sort of a cylinder whose radius would be the y value at that point and whose width would be the change in x. Right? Remembering that if I take smaller and smaller changes in x, the figure that I get will be closer and closer to this cylinder. Right. So let me draw the cylinder like this. Be something like this. So what is the volume of a cylinder? If this is R and this is H, volume of any cylinder is pi R square H. Right, just substituting my values over here, this would be pi y squared dx. Right, so now what we want to do is that, we have this certain section, and what we can do is find all the other sections too and add them all up. So the integral of pi y squared dx, let's say from point 0 to point 4, from 0 to 4. Right, so of course, generalizing it for any curve, when you rotate it around the x-axis, you can find its volume by pi integral of y squared dx. Right, so let's just get to the calculations. We took y as 2x, so 2x whole squared dx. We can take the 4 out. This would be x squared dx from 0 to 4, 0 to 4. Integral of x squared will be x cube over 3 from 0 to 4. And this would turn out to be 4 multiplied by 4 cube over 3. And this is our answer for volume. Oh, multiplied by pi. Oh, it's very easy to forget the pi out there. So there's a pi here, and a pi here. So this is our volume. And just to verify, since I took some sort of an easy figure, we know that when we rotate it, it will sort of become like a cone, right? A cone whose radius is, okay, so the value over here is 8, whose radius is 8, and this length is 4. So we know volume of a cone would be pi r square h 1 over 3. 1 over 3 pi 8 squared, and h would be 4. This is 256 over 3 pi, and this is also 256 pi over 3. All right, so let's take one more example, and let's say there's some curve, not this, some curve, something like this. It's y equals 2x squared, and let's say now instead of rotating around the x-axis, you now rotate around the y-axis a whole 360 degrees. So you would get some sort of a bowl like this once you rotate it. Right, so okay, let's leave it here, and now what you would have to do is that you would take some changes in y, and the height would be x at that point. So at any point I would get I would get a cylinder like this, and its radius will be x and width will be dy. So what I can do is I can take the volume of this, which would be pi x squared dy pi r square h, and this is the area, this is the volume of one section. I would, if I have to find it for the whole of this, I will have to sum up all of those. Right. So let's say I want to find from, let's say this is 2, so 2 times 4 will be 8, and this will be 8, right? Let's say I want to find the volume of this. What I would need to find is the integral from 0 to 8, keeping the y limits, pi x squared dy, right? And generally, if you're rotating around the y-axis, this is your formula, pi multiplied by the integral of x squared dy. Right, so as we did at the start of the video, let's make x the subject. So y is 2x squared, which means x would actually, let's make this 4. No, wait, 2 is fine, 2 is fine. So x would be y over 2, and even let's say we keep plus minus. Actually, we did not need to do this because once it gets squared, you will get the same thing back. So instead of doing this, what I can do is just make x squared the subject. So x squared is y over 2. So pi multiply the integral from 0 to 8 of y over 2 dy. Let's take the 2 outside. So pi over 2, the integral of y would be y squared over 2 from 0 to 8. Let's take 1 over 2 outside, and so this would be 8 squared. This is pi over 4 times 64, which would be 16 pi, right? And that's your answer. And remembering that the answer is basically just the volume of this bowl that you get. And you got this bowl by reflecting this around, by rotating this, sorry, by rotating this around the y-axis. Right, so this is volumes of revolution, and that wraps up integration. Till then, bye bye.